In this video, we're going to introduce gases and their physical properties. So here we have a table detailing the three states of matter: gases, liquids, and solids. The properties are listed on the side, and the type of material: gases, liquids, and solids across the top. So the different properties for shape and volume. A solid has a definite shape and volume. A liquid has a definite volume, that's what fixed volume means, but it takes the shape of their container. Now gases have no fixed volume and no fixed shape. They expand to fill the container completely. The arrangement of the particles, in a solid we have a fixed arrangement. Particles are very close together. They are held rigidly in place. In a liquid, the particles are still close together, but they are jumbled all over each other, and they have the ability to flow. In gases, we have a highly disorganized system of particles. They're far apart from each other. They're bouncing around willy-nilly. And that's why gases can expand to fill their container. The particles are just moving around quite quickly, and they're just bouncing around, and they're far apart from each other. Now, because they're far apart from each other, as opposed to a liquid and solid, the density of a gas is very low, which is much, much lower than for liquids or solids, because the particles are close together in a solid or a liquid, but in a gas they are very far apart. The movement of the particles. Gases move very, 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 very quickly. They're constantly in random rapid motion. Now, liquids, there is a random rapid motion to them. They're a little bit slower than the gases because the particles are closer together. They have to pass by one another. In a solid, the particles are moving much slower. Matter of fact, they're held rigidly in place, so all they get to do is really shake. Now, the interaction between particles. Now, this is in an ideal situation. In a solid, the interaction is very strong because the particles are held together in a three-dimensional arrangement. In a liquid, there is still strong interaction. The particles are close together. They flow past each other. It's kind of like being in a crowded subway station. You're going to be jostling past people as you move. Now, gases, there is no interaction between the particles because they are so far apart. It's kind of like being in a baseball field where there's only 9 players on the field. They're far apart from each other. You're not going to run into anybody very much. Now, whether a substance is going to exist as a solid, liquid, or a gas depends upon some interesting features. You have to have a balance between the kinetic energy of the particles, how fast they're moving. Remember, kinetic energy is equal to 1/2 mv squared, where v is velocity. So the faster moving particles, the higher the kinetic energy. And the strength of the interactions between the particles. Now, we saw that in the solid, the interactions are pretty strong. If we take a look at solid SiO2 here, the interactions that are occurring are actually covalent bonds. In liquid water here, the interactions that we see, the particles, are what we call intermolecular forces, and we're going to discuss those in a later video. But those forces, especially in liquid water, are quite strong. The interaction is quite strong. But in a gas, because the particles are so far apart, there's so much room in between individual particles, the interaction is very weak. The kinetic molecular theory of gases. And here are the main tenets of the kinetic molecular theory. Gases consist of small particles that move random, rapid motion. They're always constantly moving quite fast and quite randomly. The size of the gas particles are going to be small compared to the distance between the particles. That distance between the particles is quite large. This explains why gases are compressible. gas particles exert no attractive forces on each other. Because they're so far apart, they don't get to interact very much. And the kinetic energy of the gas particles increases with increasing temperature. Remember, we just saw that the kinetic energy is equal to 1/2 mv squared. As temperature goes up, how fast these particles move goes up. So since the velocity increases, the energy has to increase. And when gas particles collide with each other, they rebound and travel in new directions. This is what we call an elastic collision. Elastic collisions means that when they collide with something, when they bounce off themselves or they bounce off of the container that they're in, there is no transfer of energy. They just bounce off and travel in a new direction. Now, these are all properties of an ideal gas. An ideal gas is one that behaves ideally. And you're going to see in later videos, ideal gases are quite important. When we start talking about real gases, and what do I mean by a real gas? A real gas is going to have different things than this ideal. In other words, real gases will exert attractive forces. Real gases don't collide with each other without leaving some energy behind. So the real gases tend to be kind of a pain. But the nice thing about real gases is they get to be a pain at really, really low temperatures, like 5 to 50 Kelvin, or really, really high temperatures. Really high pressures. Pressures that exceed 100 atmospheres. So, for the most part, we can treat all of our gases as ideal gases. Now, the way we characterize gases, there's really 3 things we need to know about a gas. Its pressure, well, 4 things. Its pressure, its temperature, its amount, and its volume. So we know amount, that is in moles. Volume, that's pretty self-explanatory. Temperature, we understand temperature. Pressure is kind of the new one. So what is gas pressure? A pressure is a force exerted over an area. Okay? So force over area. And what this is when the particles of a gas collide with a container, they apply a force against the container. And that force is over the area of the molecule or the atom that hits the container. And since these things are moving quite rapidly, it's a fairly impressive force. Now, the units of this pressure, the force over an area, the most common one that we deal with is the atmosphere. Chemists like the atmosphere. Now, don't confuse atmosphere as in that which we breathe with atmosphere, the unit. Okay? Atmosphere, the unit, is the amount of pressure at sea level that is exerted on a column of mercury. So 1 atmosphere of pressure. That's the unit. That's not what we breathe. Now, we have some other common units. There is the millimeter of mercury. There is the torr. Now you notice 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. Well, what does that mean? Well, that means that the millimeter of mercury is the same size as the torr. So they're the same thing. Torr and millimeters of mercury are exactly the same thing. We also have the more familiar PSI. That's pounds per square inch. And it's 1 atmosphere is 14.7 psi. You'll often see PSIs listed on things like your tires. And then we have the actual SI unit, and that is the Pascal. 1 atmosphere is equal to 101,325 pascals, or 101.325 kilopascals. You'll often see the kilopascal on tires as well. So it would be good for you to have the common units memorized, particularly atmospheres, the millimeters of mercury, and your pascals. So this is the end of the video. Watch the next video to start talking about our gas laws.